Dear viewers of Bhakti.com, Biovetri from Pondicherry. Today, I am going to discuss another most important chapter in organic chemistry, biomolecules. What is biomolecules? Let me give you the definition first. Molecules that are present in biological systems are called biomolecules. Molecules that are present in biological system are called biomolecules. Important biomolecules are 1. Carbohydrates, 2. Amino acids, peptides and proteins, 3. Enzymes, 4. Vitamins and 5. Nucleic acids. So these are the important biological, that is biomolecules we will call it as. Let me go for the next. So first let me concentrate on carbohydrates. What is carbohydrates? Carbohydrates are primarily produced by chlorophyll present in plants by photosynthesis with the help of light. Let me repeat again. Carbohydrates are primarily produced by chlorophyll present in plants by photosynthesis with the help of light. Another important information here I want to convey, animals favor the backward reaction. So this is the stoichiometry of the reaction. 6 CO2 plus 6 H2O in presence of solar energy under the chlorophyll, with the help of chlorophyll, converted into 6 moles of oxygen and 6 the corresponding carbohydrates. It may be glucose, it may be fructose, it may be anything. So this is the most important information regarding carbohydrates. Right. Most of the carbohydrates have a general formula that is C dot H2OY and were considered as hydrates of carbon from where the name carbohydrates were derived. So that is was derived. So how carbohydrates name was derived? So let me repeat again. Most of the carbohydrates have a general formula C dot H2OY times and were considered as hydrates of carbon from where the name carbohydrate was derived. Specific examples: glucose and fructose are specific examples coming under the carbohydrates. So let me go in detail. It is also important to note that all the compounds conforming the formula C dot H2OY are not necessarily carbohydrate. Kindly have the precaution, that is precaution here. It is also important to note that all the compounds conforming the formula C dot H2OY are not necessarily carbohydrates. Let me give a specific example. Suppose C dot H2O one time, that is, can be represented by aldehyde, formaldehyde. So formaldehyde will satisfy this formula, which is not a carbohydrate. The same way, acetic acid represented by the formula C dot H2O twice, it's not again a carbohydrate. Thirdly, the lactic acid, hydroxy acid, it's again represented by the general formula C dot H2O 3 times, is again obeying again it is not a carbohydrate. So this is the most important information I want to convey here. The next one. Similarly, another most important information, rhamnose, another carbohydrate, the formula C6H12O5 is a carbohydrate, confirmed is a carbohydrate, but it does not fit into this definition. So this definition is not applicable to this rhamnose because it is not obeying C dot H2OY 5 times. So chemically, the carbohydrates may be defined as optically active polyhydroxyaldehydes or ketones or the compounds which produce simple such units on hydrolysis. So this is the final form of the definition for the carbohydrates. Let me repeat again. So chemically, the carbohydrates may be defined as optically active polyhydroxyaldehydes or ketone or the compounds which produce simple such units on hydrolysis. This is the actual definition. Okay, let me go for the classification of carbohydrates. Carbohydrates can be broadly classified into two types. One is sugars, another is non-sugars. Let me go in detail. First, let me take sugars. Under the sugars, what is sugars? Sugars are sweet crystalline substances and are soluble in water. So, what are sugars? Sugars are sweet crystalline substances and are soluble in water. Sugars include, specific example 1, all monosaccharides and oligosaccharides. What is oligosaccharide? Oligosaccharides is containing up to 1 to 9 units will be there. This is the most important information I want to convey. Next one. Monosaccharides are polyhydroxyaldehydes and ketones which cannot be hydrolyzed into simple sugar. This is the most important. Monohydrates are polyhydroxyaldehydes or ketones which cannot be hydrolyzed into simple sugars. So this is monohydrates. They may again classify according to the nature of carbonyl group as aldoses or ketoses. If aldehyde group is present, behaving like aldehyde, it is an aldoses. Behaving like ketone, it is a ketosis. This is the most important information I want to convey here under the classification. Okay, further, the aldoses and the ketoses are further divided into subgroups on the basis of number of carbon atoms. This is the most important classification. Number of carbon atoms in their molecules as triose, tetroses, pentoses and hexoses. Trioses, tetroses, pentoses and hexoses. Example, triose means 3 carbon atoms, tetros 4, pentose 5, hexose then 6. So aldo triose, aldo tetros, aldo pentose, aldo hexose. Same way, keto triose, keto tetros, keto pentose and keto hexose. So we can give the classification. This is the most important information. So these aldoses and ketoses may be generally represented by this following formula. So this is the aldose general formula: CHO, CHOH N times CH2OH. N may be any number starting from 1 to 6. Then here again, this is the general formula for the ketone. Again, N can be any number starting from 1 to, that is 3 or 4. That is 3. Now this is the most important information I want to give under the classification. Next one. Oligosaccharides. Next one, second part. Oligosaccharides, I already informed you, containing 2 to 9 carbon atoms. Oligosaccharides are sugars that yield 2 to 9 monosaccharides on hydrolysis and thus again classified into various groups depending upon the number of monosaccharides. This is the most important information. A specific example, disaccharides, the specific example, sucrose, molecular formula C12H22O11. It's a disaccharide. Trisaccharide, a specific example, raffinose, molecular formula C18H32O16, etc. So, oligosaccharides are sugar that yield 2 to 9 monosaccharides on hydrolysis that will produce. This is the most important information regarding oligosaccharides. Now, so what I have discussed so far regarding the sugars. So let me come for another part, non-sugars. Non-sugars or polysaccharides contain more than 10 simple units. If more than 10 units, if it is present, we will call it as polysaccharides are simply non-sugar. They are not having sweet taste. Specific example, starch and cellulose generally represented by the formula C6H10O5 to the power, that is N times. Okay, all carbohydrates are derived from D-glyceraldehyde and aldose by Cleone synthesis. This is the most important information you must know. All students, you must understand this one. Because in the laboratory, we can prepare any glucose, any carbohydrate starting from D-glyceraldehyde or L-glyceraldehyde. What is D, what is L? I kindly refer my lecture regarding configuration. Okay, let me go for the next one. What is Cleone synthesis? Under the Cleone synthesis, so there are a few steps are involved. So starting from the three-membered the aldotriose converted into four-membered aldotetrose. So I am giving here the specific example. So this is a D-glyceraldehyde. Why it is D? All the negative group, OH group on the right hand side, this is D-glyceraldehyde. Glyceraldehyde. So this D-glyceraldehydes, when you treat with HCl, so it undergoes addition reaction to produce corresponding cyanohydrine. That means glyceraldehyde cyanohydrine. So there are two possibilities. That means OH groups enter here in the right hand side, or that is the OH group will be coming on the right hand side. This is the way it can be. There are two possibilities it can. So what will happen now because of this one? So we are getting two different configurations. The interesting information. Right. Now, what will happen now? This, under the second step, after the formation of these two, the corresponding link, so we are now, the cyanide we are hydrolyzing. On hydrolysis, the cyanide will give the corresponding acid containing 4 carbon atoms. So carbon 1, carbon 2, carbon 3, carbon 4. 4 carbon atom, the corresponding acid. So cyanohydrine on hydrolysis produces the correspondingly the acids. So now these acids, what will happen next step? An action of heat produces a cyclic anhydride. It produces a cyclic anhydride. In the next step, this cyclic anhydride, what is happening? Undergoes reduction process of lithium aluminum hydride producing aldehyde. So we are getting 2 aldehydes. That's again. So these two aldehydes, that is the corresponding carbohydrates, now is containing 4 carbon atoms, but they are having a different configuration. The first case, 2 OH groups on the same side. The second case, 2 OH groups on the opposite side. So they both again are nothing but aldotetrose. Kindly follow. This is the most important information. So what we can do by Cleone synthesis, any lower number can be converted into higher number. This is the most important information I want to convey here. Next one. So let me concentrate now. Under the monosaccharide, the first member I am going to take glucose. I want to discuss regarding glucose, which is a monosaccharide. Glucose occurs freely in nature as well as in the combined form. It is present in sweet fruits and honey. This is the most important information. So let me discuss first prepare. How we can prepare in the laboratory? It can be prepared from sucrose by the laboratory method and starch by commercial method. Let me discuss one by one. First, let me take the preparation of glucose from sucrose by laboratory method. So from cane sugar, that is nothing but sucrose, you can prepare in the laboratory. So it is prepared in the laboratory by hydrolysis of cane sugar in the presence of alcohol by dilute acid. HCl or sulfuric acid can be used. So cane sugar, nothing but sucrose. When you treat with water in presence of acid, converted into glucose and fructose. Both are having the same molecular formula, C6H12O6. This is the most important information. The second one, Again, glucose can be prepared from starch, which is nothing but a commercial method, large scale, industrial method. Under this method, so it is prepared commercially by hydrolysis of starch by boiling it with dilute aqueous solution in sulfuric acid at 393 Kelvin under pressure, 2 to 3 atmospheric pressure. So corresponding stoichiometry, C6, this is molecular formula for starch, C6H10O5 N times. Then N, it takes N times of water if you add, and if you treat with an acid HCl and sulfuric acid, we are getting N molecules of glucose, C6H12O6, nothing but glucose. So glucose, we are getting large number from starch. So purely number of glucose unit depending upon the molecular mass of the starch. That is the most important information here. So next let me go for the structure of glucose. So first I have discussed how it is prepared in the laboratory. Now let me discuss how the glucose structure can be determined. Both point of view, this is normally most important. Number one, there are a number of steps there. First step, step 1, elemental analysis and molecular weight determination show that the molecular formula of glucose is C6H12O6. What do you mean by elemental analysis? That means determination of carbon, determination of hydrogen, determination of oxygen. Like that, if you determine reduction and followed by estimation, then we can identify the empirical formula and molecular formula we can identify. So from the molecular weight, we can determine the molecular formula as C6H12O6. Well, let me repeat again. Elemental analysis and molecular weight determination show that the molecular formula of glucose is C6H12O6. Step 2. So glucose on reduction with corn HI, hydroiodic acid, in presence of red phosphorus produces NXA. NXA. So NXA molecular formula here it is given already. CH3, CH2, 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 CH3. NXA. So it is coming from glucose. What way? On treatment corn HI and in presence of red phosphorus. So this information, this is the most important information. So what you are getting in the conclusion from this reaction. This indicates that there are 6 carbon in the glucose molecule. Very clear. Because NXA, 6 carbon in the glucose as unbranched chain. This is another information we are getting. Unbranched chain. So this indicates that there are 6 carbon in the glucose molecule as unbranched chain because formation of NXA it is there. Okay, so step 3. Further, glucose undergoes additional reactions with 1 mole of HCl and condensation reaction with 1 mole of ammonium, that is hydroxylamine or phenyl. So from these reactions indicate the presence of a carbonyl group. These are the characteristics of a carbonyl group. Maybe an aldehyde group or keto group, but important information, both will not be there, but not both. Either aldehyde or keto group may be present. Only if it is present, then it will undergo these addition reaction as well as condensation reactions. Next one. Glucose readily dissolves in water to give a neutral solution. Take glucose, add water and just test the acidity or basicity. It is a neutral. This indicates that the glucose molecule does not contain a carboxyl group because we know already oxygen number is higher. So when oxygen number is higher, we have to identify whether it is an acid or not. So it is not an acid. This is the interesting information. So this indicates that glucose molecule does not contain carboxyl group. Next one. Step 5. Glucose reacts with acetic anhydride in the presence of pyridine to form pentaacetate. Pentaacetate. So this pentaacetate can be determined from the molecular weight determination. So from the mass spectrum, this we can identify. This reaction indicates the presence of 5 hydroxyl groups. So 1 OH group, 1 acetate, 5 OH group means 5 acetate. So pentaacetate. Since glucose exists as a stable compound, because it is a stable, it indicates that 5 OH groups should be attached to 5 different carbon atoms. This is the most important information. If two OH groups are present in the same carbon atom, it will not be stable. Since it is a stable, it means it indicates that the 5 OH groups should be attached to 5 different carbon atoms. This is the most important information regarding structure. The next one, step 6. Glucose on mild oxidation with the bromine water forms gluconic acid. So bromine water is a powerful oxidizing agent, that is a powerful oxidizing enough to oxidize glucose to gluconic acid. Whereas the same glucose with the concentrated nitric acid gives saccharic acid, dicarboxylic acid. This is the interesting information. So this is the structure of gluconic acid. So bottom CH2OH, the top COH group. So kindly see, this is the gluconic acid. Whereas here it is the dicarboxylic acid, it is saccharic acid again containing, that is 6th carbon atom. Kindly follow. So one is gluconic acid on with the bromine water, saccharic acid with the nitric acid. So what information we are getting from this one? Formation of gluconic acid. Top COH, bottom CH2OH. Formation of gluconic acid indicates the presence of an aldehyde group. Since only aldehyde group can be oxidized to an acid by gaining one oxygen atom without losing hydrogen atoms. This is the proof. So that may be an aldehyde group. Kindly follow. Right. Formation of saccharic acid, that is a dicarboxylic acid, the 2 COH groups, indicates that the presence of a primary alcoholic group at the other end. Bottom, there is a primary alcohol. Only if there is a primary alcoholic group, then again this is possible. So these are the two information we are getting from the step 6. Step 7. Glucose reduces tolerance reagent, ammoniacal silver nitrate, to metallic silver, bright silver, and the filling solution to red cuprous oxide. This is the characteristic test for carbohydrates. So glucose reduces tolerance as well as filling solution. So these reactions further confirm the presence of an aldehyde group. We have already proved that there is an aldehyde, there may be an aldehyde group. So again it is proved by the reactions in step 7. Hence, from the above discussion, so far what I have discussed, and from the configuration of gluconic acid and saccharic acid, the open chain structure of glucose can be represented as follows. This is the open chain structure, exact configuration. CHO, CHOH, 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 and CH2OH. So this is carbon 1 CHO, carbon 2 OH on the right hand side, carbon 3 OH on the left hand side, carbon 4 OH on the right hand side, carbon 5 OH on the right hand side, and finally carbon 6 CH2OH. This is glucose structure, open chain structure. But kindly follow, this is not true. Let me explain how it is. Glucose does not answer for Stiff's test, and glucose pentaacetate does not react with hydroxylamine. Kindly follow. What is Stiff's test? Stiff's test is normally used to test the presence of an aldehyde group. Aldehyde group will give you a violet color. Normally will give. So, but here glucose is not answering. So that means there is no free aldehyde group. And another, the pentaacetate is not answering for, again, react with hydroxylamine. It's not undergoing condensation. So this shows that there is no free aldehyde group present in the glucose. Hence, the more suitable cyclic structure for glucose may be represented. So yes, a cyclic structure may be suggested as follows. Instead of the free aldehyde group, so the glucose will be in this form, but it is behaving like an aldehyde, that's all. So this linkage, we'll call it as hemiacetal linkage. Hemiacetal linkage, easily breakable. Even if you place it in water, it will break and will behave like a open chain structure. This is the most important information I want to give here. Step 9. Glucose is found to exist in two different crystalline optically active forms as D-glucose, specific rotation plus 113 degree, and beta D-glucose, that is alpha D-glucose plus 113 degree, and beta D-glucose plus 19 degree. So there are two different forms. Glucose exists in two forms. The above facts would not explain the open chain structure of glucose. So again, this is opposing the open chain structure. So a closed chain structure only we are suggesting. A more suitable cyclic structure of glucose can be represented as follows. So more probable the cyclic structure will be as follows. So this is the actual structure for alpha D glucose and beta. This is alpha D glucose, this is beta D glucose. Dear students, you can raise a question. That means what is alpha, what is beta? So numbering let me give now, starting from this 1, 2, 3, 4, 5 and 6. So in the first carbon atom, if OH group is below, it is alpha. If OH group is above the ring, it is beta. This is the most important information. If you construct a model, this you can easily observe. If OH group is below the ring, it is alpha D glucose. Above the ring, it is beta D glucose. This is so glucose exists in two forms, alpha D glucose and beta D glucose. So these two glucose, nothing but we'll call it as anomers. We'll be discussing later. So alpha D glucose and beta D glucose are called anomers. Okay. So far what I have discussed regarding structure of glucose. Next, let me go for the structure of fructose. It's a ketose structure. It's a ketose. Okay. Let me again start there. How the structure of fructose can be defined. Now, step 1. Elemental analysis and molecular weight determination show that molecular formula for fructose is again C6H12O6. Again, as usual, elemental analysis, carbon detection and followed by estimation. Molecular weight from the mass spectrum. So that you will get information, the formula should be C6H12O6. The second step, fructose on reduction with corn HI in presence of red phosphate again produces an hexane, as is in the case of the glucose. So what will happen on this information, since this N-hexane is formed from fructose also, so this indicates that there are 6 carbon atoms in the fructose molecule as unbranched chain. Okay, step 3. Further, the fructose undergoes addition reaction with 1 mole of HCl and the condensation reaction with 1 mole of hydroxylamine or phenyl hydrogen. So these reactions indicate the presence of a carbonyl group, an aldehyde or keto group, but not both. It may be an aldehyde group or keto group, but both will not be simultaneously present. This is the important information. Next one, step 4. Fructose readily dissolves in water to give neutral solution, as in the case of glucose. So this indicates that fructose molecule does not contain the carboxyl group. Another most important information. Like glucose, it is not also an acid. Step 5. Fructose reacts with acetic anhydride in the presence of pyridine to form pentaacetate, as in the case of glucose. This reaction indicates the presence of 5 hydroxyl groups. Right. Since fructose exists as a stable compound, as in the case of glucose again, it indicates that 5 OH groups should be attached to 5 different carbon atoms. It is exactly similar to that of glucose. So 5 OH groups are present confirmed, but it is not the different. It is present at the 5 different carbon atoms. The next one, step 6. Fructose does not react with the mild oxidizing agent such as bromine water. We have already discussed glucose on reacts with the bromine water gives gluconic acid. But in this case, it does not react because it is not easily oxidized. Whereas, but with the nitric acid, it gives a mixture of glycolic acid and tartaric acid, mixture of 2 acids containing less number of carbon atoms. This is the most important information. So here only you can get the idea regarding the structural difference between glucose and fructose. So formation of glycolic acid and tartaric acid now gives a very clear idea. So this is glycolic acid, COOH, CH2OH, and this is tartaric acid, COOH, CHOH, CHOH, COOH, tartaric acid. So formation of glycolic acid and formation of tartaric acid shows that there is a keto group in fructose. Only if there is a keto group, this is the possibility. Very clear idea. So that's why you call it as fructose and ketose. When fructose is treated with HCN, it forms an addition product which upon hydrolysis and subsequent reduction with HI and red phosphorus gives 2-methyl-hexanoic acid. This indicates that keto group is adjacent to one of the terminal carbon atoms. This indicates that keto group is adjacent to one of the terminal carbon atoms. This is the most important information I want to convey. Step 8. When fructose is treated with sodium amalgam and water, it undergoes reduction to give a mixture of 2 alcohols, sorbitol and mannitols. The both structures are given below. This further confirms that the keto group is adjacent to one of the terminal carbon atoms. So it is adjacent to one of the terminal carbon atoms, either it is in the second carbon atom. So this is the structure of sorbitol, kindly follow. Sorbitol, this is the structure of mannitol. The only difference here is, kindly follow, up to this, it is common. The difference lies only at the top one. That is, in the sorbitol OH on the right hand side, in the mannitol OH on the left hand side. That is the main difference. So this is possible only if there is any keto group present in the second carbon atom. This is very, very interesting information. Hence, from the above discussions and from the configuration of glycolic acid and tartaric acid, the open chain structure of fructose can be represented as this structure. So we are getting glycolic acid, we are getting tartaric acid, we have discussed already. So from this we can now be able to write the open chain structure of fructose is as follows. CH2OH, CO, CHOOH, 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 CH2OH. Okay, the next one. Fructose does not answer for CO group. Because when there is a carbonyl group means, CO group means, it should react like the CO group, ketose. But it is not answering. And the pentose state again, as usual, does not react with hydroxylamine. So this shows that there is no free keto group in the fructose. Like in the case of the glucose, there is no free aldehyd group. The same in the fructose, there is no free keto group. Hence, the more suitable structure for fructose may be this one or this one. Kindly follow. Two possibilities. Okay, let me go for the further. Alternatively, fructose is lever rotatory. This is another interesting information. Glucose is dextrorotatory, whereas the fructose is lever rotatory. The more suitable two cyclic structures of fructose can be represented as follows. Kindly see the structure of fructose. This is structure 1, this is structure 2. This is alpha D fructopyridose, this is beta D fructopyridose. As usual, alpha OH below the ring, beta that is OH above the ring. So D indicates that the lowermost the optical active compound, the negative part on the right hand side. Not to have a clear idea regarding D and L configuration, refer my previous lectures. So this is alpha D fructose left side and beta D fructose on the right hand side. Now, next let me go for sucrose, a disaccharide. Sucrose, a disaccharide. Sucrose having the molecular formula C12H22O11 is the commonest sugar is known. Is a commonest sugar is known. The most important sources are cane sugar and sugar beets. It is a colorless, odorless, crystalline compound. It is soluble in water, freely soluble in water. It is texturitatory. It is a non-reducing sugar. This is the most important information. Non-reducing sugar, as it does not reduce tolerance and swellings. We have seen already glucose and fructose reduce tolerance and swelling, whereas sucrose will not reduce tolerance and swellings. Sucrose, on heating slowly, carefully, melts and when allowed to cool, it solidifies to pale yellow glassy mass called barley sugar. This is the other interesting from barley sugar. The same sucrose, when heated to 200 degrees centigrade, it loses water to form brown amorphous mass called caramel. This is another interesting information. Sucrose on hydrolysis gives equimolar mixture of D plus glucose and D minus fructose. One is texturotatory, another is minus the lever rotatory. So glucose is texturotatory and fructose is lever rotatory. So equal quantity. These monosaccharides are held together by glycosidic linkages between C1 of alpha D glucose and C2 of beta D fructose. That means glucose and fructose are connected by C1 of alpha D glucose and C2 of beta D fructose. It's a disaccharide. Now, let me go for structure of sucrose. Let me discuss regarding the structure of sucrose. Elemental analysis and molecular weight determination show that the molecular formula of sucrose is C12H22O11. This is as usual. Step 2. Sucrose reacts with acetic anhydride in presence of pyridine to form octaacetate. This reaction indicates the presence of 8 hydroxyl group in sucrose. Step 3. Since sucrose exists as a stable compound, it indicates that 8 OH groups should be attached to 8 different carbon atoms. As in the case of glucose and fructose, here also all the 8 OH groups are present in the 8 different carbon atoms. Next step, 4. Hydrolysis of sucrose with the dilute acids yield an equal molar mixture of alpha D glucose and beta D fructose. Kindly follow, this is the most important information you must know. Hydrolysis of sucrose with the dilute acids yield an equimolar ratio mixture of alpha D glucose and beta D fructose. So glucose in the form of alpha D, fructose in the form of beta D. Right. This indicates that the sucrose molecule is made up of 1 unit of each monosaccharide. Now step 5. Sucrose does not reduce tolerance reagent to metallic silver and failing solution to red cuprous oxide. It's a non-reducing sugar. It does not form ozone. Ozone is it's the compound formed from From glucose and for fructose, if you treat phenylate as hydrochloride, it will produce a mosazone. But this sucrose, it does not form mosazone. These reactions further confirm that glucose and fructose are joined through C1 in glucose pyranose form and C2 in fructose furanose form. This is the most important information regarding structure of sucrose you must know. Hence, from the above step 5, above discussions, the structure of sucrose can be represented as, in the cyclic form, is as follows. So this is the structure of sucrose. That means glucose in the form of alpha and fructose in the form of beta. So it is a mixture of alpha D glucose and beta D fructose joined together. So it is joined through the second carbon atom, or in the case of fructose, so we will cut a sucrose. That's why it is acting as a non-reducing sugar. Can you follow? So other important disaccharides I want to mention here. One is lactose. Beta galactose, normally 1,4 beta glucose. That means both one side galactose and other side glucose. In the galactose side, C1 carbon. In the glucose side, C4 carbon connected. That we will call it as lactose. Maltose, another disaccharide. Again, alpha glucose, and there is again alpha glucose. That means in both cases, glucose the C1 and C4 of alpha D glucose, that is connected, we'll call it as maltose. Coming for cellulobiose, it is beta D glucose in both cases, and C1 and C4 it is connected. This is glucose. So the structure, if you want, you can see here. So this is the lactose, beta D galactose, beta D glucose structure, and this is maltose, alpha glucose and alpha glucose, it is connected, and this is the structure of cellulobiose, both cases beta D glucose connected, C1 and C, that is here it is C1, this is here it is C4 connected. These are all disaccharides. Next, let me concentrate on polysaccharides. Polysaccharides are polymers of monosaccharides. The most important polysaccharides are starch and cellulose. They have general formula C6H10O5 N times. The bracket N times. The general formula you can use for starch as well as for cellulose. Starch is the main storage of polysaccharide of plants. It is a white amorphous substance with no taste or smell, non-sugar. Starch is present in wheat, corn, barley, rice, potatoes, nuts, etc., etc., etc. It is present there. Next one. Starch is a mixture of two polysaccharides, amylose and amylopectin. That means amylose, that if you hydrolyze partially the starch, it will be a mixture of amylose and amylopectin. What is amylose? Amylose is a straight chain polysaccharide with alpha D glucose units held by C1 and C4 glycosidic linkage, whereas amylopectin is a branched chain polysaccharide with the same linkage. So amylose, straight chain, linear chain, and whereas amylopectin, it is a branched chain. This is the only difference in structure. Starch solution gives a blue color with a drop of iodine. So we can use as an indicator in the titration of iodometry. The blue color is due to the formation of an inclusion of complex between iodine and amylose fraction of starch. This is the interesting information. When heated to temperature 200 to 250 degrees centigrade, it changes into dextrine. It is changed into, that means starch will be converted into dextrine when you heat it to 200 to 250 degrees centigrade. You can see the here. the stoichiometry. C6H10O5 N times starch, and again giving C6H10O5 but the structure is different, extreme. Now, when boiled with the dilute acid, starch ultimately yields glucose via maltose. With the enzyme diastase, it yields maltose. That means starch is giving again maltose in presence of the enzyme diastase. This is the another interesting information regarding the polysaccharide. Now, cellulose. Next, let me go for cellulose. Cellulose is found in all plants, and so it is most abundant of all carbohydrates. It is the material used to form cell walls and other structural features. So cell walls and other structural features are made up of the corresponding cellulose. It is insoluble in water and all organic solvents. When boiled with dilute sulfuric acid, it is completely hydrolyzed into D-glucose. Very, very interesting. From cellulose, on hydrolysis with dilute sulfuric acid, final product will be, ultimate product will be D-glucose. Next one. So, I hope you have enjoyed the lecture. Thank you.